Hello, my friend, and welcome back to our second in a series of master classes from the very people who process the images from the James Webb Space Telescope. In our last video, astronomer Elisa Pagan showed us how she downloaded the raw images from the Webb Data Archive and turned them into this dramatic image of the Carina Nebula. In today's video, her colleague Joe DePasquale is going to show us how he processed this image of SMACS 0723, better known as Webb's First Deep Field. And as you can see, this is a pretty long video. So I invite you to make use of the chapters. Feel free to use them to jump around. And I also invite you to download Joe and Elisa's Photoshop files so that you can open them up in either Photoshop or GIMP, and you can see exactly what they did and kind of follow along in real time with the video. And so without any further ado, I bring you Joe DePasquale and Webb's First Deep Field. Joe, thank you so much for showing us how you did the Webb Deep Field, or the Webb's First Deep Field, I guess the first of many deep fields. I understand, though, you use a very different kind of workflow, and I was hoping you could show us that today.
Yes, sure. So, Elisa and I do have different approaches to the way that we process images, and I encourage that. I think it's a really good thing to have different approaches because we come at it from a different perspective. I've been working for a long time in PixInsight, and it's just something that I'm really comfortable working in, and it lends itself to certain types of images really well. I really like its ability to do accurate color calibration of images. And so for the deep field image, I did use a combination of PixInsight and Photoshop. That's sort of my typical workflow, is to start with PixInsight, get to a nice color image, and then bring it into Photoshop for the sort of the post-processing and getting it ready for publication. And so I'm going to jump in from the start here, actually, and kind of give you an overview of how I process the deep field image, starting with mast.stsci.edu. So if you're interested in trying your own hand at processing the deep field image, you would start here. I've got a few tabs here so that I don't have to do the searches that I've already done. So I would normally click advanced search. And also I'll point out that I'm not logged in. I work for Space Telescope, so I have privileged access to the archive. But I'm not doing that here. I want to show you that as an anonymous user, I have full access to the deep field data from Webb. Okay, so the next tab here is just doing the advanced search. I've already entered the information, the relevant information here, SMACS 0723. That's our deep field cluster that we observed for the early release observations. I'm setting the mission to JWST. Also, you can see that once I've entered an object name here, MAST automatically solves the name and finds the coordinates on the sky. So the Arraying deck is already populated. And so we're already doing a cone search of just like a very small portion of the sky. So then I've narrowed it down to just JWST data and the NIRCam instrument. And after it's gone through the entire archive of everything using those filters, it has found 6 records, which makes sense to me because I know that we observed SMACS 0723 with 6 filters on the NIRCam instrument. So I'll go to my next tab, which shows you this would be the results after doing that search and performing the search through MAST. You get your 6 filters here. If I scroll over, you can actually see the filter names. These filter names are linked to the wavelength. It's the central wavelength of each filter. And so 0.9, this would be 0.9 micron. The filter names they're sort of following an older naming convention from Hubble filters. But because we're talking about everything is listed in nanometers. So technically this would be 900 nanometers. This would be 1500 nanometers. But to keep the filter names smaller, they're basically divided by 10. It's not uniform across all the different filters. Like Hubble doesn't do that. So it can be confusing, but if you just remember that this is sort of nanometers divided by 10, that's kind of what you're getting here. And if you click on album view, you actually get a quick preview of the image that you'll be downloading. And so you might be wondering why there's 2 boxes here for each of these images. And it's actually because the way the NIRCam instrument is set up, it's 2 different detectors. Each one of those has 4 cameras in it. And because of the way we observed the deep field, we knew we would have sort of an extra bit of sky. We call it a parallel field. And we didn't use it for the release, but it's there. It's in the archive, and it's available to process if you're interested. And it's demonstrated here in these 2 boxes in the Astro view. Okay, so I've already downloaded all these files. And one thing I want to point out to you, if you've downloaded them from MAST, they're going to be large. I did go through and extract the images from those files, and I'll explain what that means in a second. But I just want to point out that 3 of these files are nearly 200 megabytes in size, and then the other 3 are 47 megabytes in size. And that right there is an indication of a sort of a quirk of the NIRCam instrument, is that the short wavelength filters are higher resolution by about a factor of 2 than the long wavelength filters. So one of the first things you're going to have to do when you download the data is to register everything to a common reference frame and to get all of your images at the same resolution. I would typically upscale the long wavelength filters to match the short wavelength filters, because the short wavelength filters look amazing, and you can upscale the long wavelength filters without losing too much information and have them match the short wavelengths. Okay, so I'm going to bring up PixInsight now. This would be the next step in the process. PixInsight will allow us to bring the files in and take a look at them and then start working on them. Okay, so we've got PixInsight up, and I've got the files that I've downloaded from MAST here. I'm going to bring one of them in because I want to demonstrate one quirk of downloading files from MAST, which is that a FITS file is the file format that is used in astronomy and astronomical imaging, and it stands for Flexible Image Transport System. Now, FITS file is not just an image file. It can contain many different files. It's sort of a package file that contains a bunch of stuff in it. And so when you download images from MAST, you're not only getting the image, you're also getting a bunch of calibration files that come along with the image. This would be like masks that were used for putting together mosaics, noise, flat fielding, all that stuff is included in here. And you may want to use that, but for what we're doing, these images have already been calibrated. They've been fully run through the pipeline. And so we don't need to worry about that stuff. So we would just bring the image in and then close out these windows. You can just do it one by clicking, or, PixInsight has some abilities to run commands. I would maybe do close *var, and that'll close all windows that have var in the name. That was, I think, only one. So we'll close all of them. And then we're left with just the image file. And you can see the _SCI science. That means science image. So that's the relevant file that we want, or the image that we want out of the FITS file. I've already done this for all of the images, so I'm going to open those up here. I've saved them out as separate files, so I can always come back to them if I need to. And I'm going to bring them into PixInsight. Okay, here we go. All right, so now we're opening all 6 image files, and now we're looking at, see, the SCI is _SCI is there for every single one of these. So now I know that I'm looking at science image files across the board. And now this is where the aspect of the imaging that I mentioned, the NIRCam instrument having different resolutions for your different data, this is where that comes into play. You can see the second marker here, 1.4, 1.6, 1.6, 1.13. That's just an indication of the zoom level currently in the image. And the fact that they're all basically the same size in the window, but they each have different zoom levels, tells me that we're actually looking at different resolutions across the board here. And that makes sense, because I know that the short wavelength channels of NIRCam are about twice the resolution of the long wavelength channels. So the first step that I want to do here is to register all the images together. And of course, I probably want to see what's in there, right? So I want to run some kind of tool that would allow me to see what the image data contains. And PixInsight has a great tool for this. It's called the screen transfer function. This will raise the pixel values in an intelligent way. It actually goes in and evaluates all the pixel values across the image and stretches them in a way that makes sense to allow the user to see what's in the data without actually changing anything in the image. And so I'm going to run the screen transfer function using a shortcut, Command A, that just applies it to the current active window. And what I see here is that there's some clipping, and that is because the default bit depth when an image is rendered to screen can be, it's not quite deep enough. It's not, the bit resolution is not high enough for me to actually see all the details in the image. So I've just changed that with this little window up here where I go to 24-bit. This applies the screen transfer function using a 24-bit lookup table. And so now I can see more details in the image. And I can also see that this is the galaxy cluster SMAX 0723, and this is our parallel field over here. Now I know that I want to register all the images to each other. And so the next step would be to use a tool called, so I go to the process menu, image registration, star alignment. What this tool will do is allow me to set up a reference image. And for that, I'm going to use my shortest wavelength channel, which is the 090W. I'm going to make that my reference image, and then I'm going to scale everything else up to it. So I will click Add Views, which gives me a window that shows all the active windows that are open right now. I'm going to select all and then deselect 090 because that's already the reference. Hit OK. And then I need to run this tool. And the way that PixInsight has this little setup down here, to run tools, you either click the box or you click the circle. The box applies the current tool to the currently active window. The circle applies it to everything that's open right now. And since I'm registering all the images that are open, I'm going to click the circle. So now star alignment is running through evaluating the reference image, finding all the stars that it can in that image, and then checking the reference or the target images and looking for matches between them. And once it finds a good match, it'll look for a few matches, and then it will apply a transform to the target image that it's currently working on and scale it to match exactly the reference image. And this works really well, especially for a field like this that's just full of stars and galaxies. There's a lot of point sources for this tool to find and use as references. So now I know that all of the images that it just generated are matched up exactly to the reference image, the 09OW. So I'm going to apply my screen transfer function again, just so I can see what I'm working with. Change that to 24-bit. Okay, that looks great. I'm going to rename all of these windows because they're going to be really hard to reference later if I keep them with the current names, all this extra information in it. So I double click on that tab, and I just want to name them according to the filter name. So I'm going to change this to F444W. And then I'm going to do this for the same thing for the F356, F277, F200, F150. Now I'm up to the images that I had already opened that I then scaled up to match the 09OW. So I'm actually going to close all these because I don't need them anymore. And the last one that I do need is, of course, the F09OW. So now that I have all of my windows here, they're all matched exactly, I can start attempting to apply color to them. And the way that I do that with PixInsight is using a tool called Pixel Math. This is a very powerful tool that allows you to sort of slice and dice open images as you wish. What I'm going to use it for is to make a color combination of all the open images right now. And the way that we apply color to these images, as I've mentioned before, is a chromatic ordering of color. And so I'm taking my longest wavelengths and assigning those to red, and my shortest wavelengths to blue, and everything in between is green. With 6 filters, it works out really nicely that you can add 2 filters per color channel. So I know that I've got RG and B color channels, and I need to define how I'm going to combine the different filters to create those color channels. So the first thing I need to do is to uncheck this box here, use a single RGBK expression. I don't want that because I want to be able to define each color channel individually. I also need to click this destination region here and change a couple of things here so that when I process the data, it will do what I want it to do. And that is I need to create a new image instead of replacing the target image. And I want that new image to be in an RGB color space as opposed to a grayscale image. And so now I can define what those color channels are going to be. And this is where it's really helpful to change the names, the working names of those files, because I can just reference them directly in Pixel Math this way. And so I want my red channel to be a combination of the 2 longest wavelengths. I'm going to do F444W plus F356W. And it's really that simple. I'm just telling it these 2 open files, add them together. But I need to do a little more because I don't want them to just add together and create like a double red channel. I actually need to give them equal weight. And so I'm going to divide by 2. So I'll put parentheses around this and then divide by 2. And that gives equal weight to both F444 and F356 in the red channel. For green, I'm going to use the next longest wavelength filters. So F277W plus F200W divided by 2. And then for blue, the next set of filters, which are my shortest wavelengths. And now I'm just going to apply that. You'll notice I'm hitting the box here. For some reason, Pixel Math doesn't like when you apply things globally. It doesn't really understand that because you're kind of already defining things in a global setting by referencing them through the color channels. So clicking the box, because I have it set to create a new image, it'll act as if it's running globally. I know this is a little confusing, but it works. So let's just run it. And the resulting color image shows up here as image 12. And again, we haven't stretched the data yet, so I have to apply the screen transfer function. And what we'll see is colors might look a little strange, and I can explain that in a second. I need to change the bit depth again so that we can see this better. Okay, So that excess purple that we're seeing is a result of the image not being color balanced. And I'm applying the screen transfer function in such a way that with this button here, the R, G, and B channels are actually linked together so they can only move as a group. And so if you stretch it and the image has not been color balanced yet, you may get excess color coming from some of the filters and not others. And so in this case, the red filters are sort of taking over. It's a combination of the red, and so the short and the long wavelength channels are, there's an excess background in them. So I'm going to unlink those channels and apply the screen transfer again. And this looks a little more natural to me. And you can see that we have like a really nice looking color image across both fields. They do look a little bit different because, again, the image has not been color balanced yet. And I'm going to crop this image to just focus in on the galaxy cluster. This is a beautiful image in itself as well, but I just want to keep my focus on the galaxy cluster for now. So I'm going to use a tool under the geometry menu called dynamic crop. And I click on the image to initiate it. And then we're going to just pull this box over here, and that defines the crop region. I'm going to crop up from the bottom a little bit as well. Get rid of some of that black space. And then I just hit the check mark, and the image is cropped. Close that out. I'm going to reapply my screen transfer function just to see if anything changes. It does a little bit because it evaluates the whole image. If there's less black space, that will change a little bit how the screen transfer function works. Okay, so now I can see I've got a really nice looking color image, but it's not ideal in terms of the color balance. I see some excess green across the entire field. I'm also seeing some of the calibration issues in the short wavelength channels showing up in the form of these blue boxes. This was a mosaic, so there's a 2x2 across this field. And in some of the regions, the background levels in the short wavelength channels are a little higher. And so you basically have like a pedestal of excess blue light in those regions. It's not exactly a pedestal. It actually varies across the detector, and it varies across exposures. So it's a little tricky to get rid of. It's not as simple as just subtracting a box from this region. It's a little more nuanced than that. And it's a step that I will need to take later on when I'm working in Photoshop. But for now, I do want to concentrate on getting a nice color balance for this image. And so the first step towards doing that is to define a neutral background region. So I'm going to create a preview region within this image. And that's what this little box is here, new preview. So I click on that, and then I'm going to zoom in to the image, move around a little bit. I'm looking for essentially just a blank area of sky. So something like this or down here. And the reason I'm sort of honing in on this region of the image is because the background variations from the short wavelength channels are sort of minimal in this region here. So I'm going to treat this as my sky background reference. So I'm going to define a box in here. Zoom in too far. Okay. We'll go maybe something like that. And we'll use this as the reference for our background. And I can actually see when I create a preview, I can actually see it here. So you can see it's a pretty clean region of the sky. And so I'm going to go into the process color calibration background neutralization menu here. And I bring up this box. I'm going to tell it to use as a reference image the preview that I just defined within our image. And the way I do that is click this box and then select image 12, preview 1. Hit OK. And what this is going to do is take all the pixels in that preview region and evaluate their color values and try to get everything to be a neutral gray. So when I apply that to the image, it's going to change everything, okay? Because now image pixel values have actually changed, and our screen transfer function is now, it's what it was before. And so after the change in the pixel values, it hasn't caught up yet. So we're going to reapply screen transfer function. Okay, we've done that. It's not going to look much different yet because we haven't actually really done a full color calibration. If I link the channels, we might see a change. Yeah. Okay, so with the channels linked, we do actually see that the background region is a neutral gray, as neutral as it can get. And colors are starting to look a little more natural. I still do see this sort of green cast across the entire image. And of course, the blue, the excess blue in these regions here. So the next step is to do the full color calibration. And for an image like this, what I really like to do is search out any of the face-on spiral galaxies that show up in this image. I want to use this spiral galaxy as my weight reference because spiral galaxies contain all populations of stars from young to old. And that represents all the possible colors of stars. And so if you use an entire spiral galaxy as your white reference, everything else will fall into place in terms of the color balance. So I'm going to go into the image and look for nice face-on spiral galaxies like this one that I'm zooming in on here. I will have to account for the fact that there's an excess blue here, so I'm going to find some other spiral galaxies outside of this region. I'm just moving around the image now, looking for more galaxies to use as a reference. This one here looks really nice. I will define another preview window around it. And up here, this guy, I don't want to get this diffraction spike in there, so I'm just going to take about half of this galaxy and use that as a weight reference. Okay, so now at this point, I've defined a few previews. Christian, you're muted, I think.
Sorry about that question, Joe.
Yeah.
So how is it that you're choosing to use the galaxies versus the stars themselves? Because, I mean, to me, they look pretty white. Is that really the case, though?
So in this case, I'm looking for galaxies that are roughly the same color as the cluster is showing up across the image. Mm-hmm. And I could use stars, but the stars do have an inherent color to them that I don't necessarily know what that is right away. But I know if I use a spiral galaxy that I sort of collect all the colors that I can possibly get, if that makes sense. So using that as a weight reference, then everything else will sort of fall into place from there.
Oh, okay. Thanks. All right. That makes a lot of sense.
Yeah.
Absolutely.
Okay. All right. So as I was saying, I've got the 3 different preview windows open for the different galaxies, and I can actually look at them here like this. There is no way to reference multiple previews when you're running this color calibration tool. So the first thing I need to do before I start running color calibration is another tool, which comes under the script menu. It's a script called Preview Aggregator. It comes under Script, Utilities, Preview Aggregator. And all it does is it will look at the current open image and see how many different preview windows are in there. I don't want to take the first one because I know that's my background. So I just want the 3 that I defined around galaxies, and hit OK. And what that does is it creates a new image window that is just the galaxies. So now we have this single image represents the 3 spiral galaxies that we've chosen as our white reference. And so if I go to Process, Color Calibration, this is where I will define that white reference. I want to reference the aggregate image. So I will select that, aggregated. I'm going to turn off structure detection because one of the things color calibration can do is actually evaluate the entire image and look for stars and then use the stars as your white reference. But we're not doing that here. We're just using the whole galaxy as white reference. So I'll turn that off. And I do need to go back and reference the original background region. So that preview 1 that we used when we were doing background neutralization, that's another reference for color calibration. Okay, so now that I have everything defined, I will run this on the image 12. I'm going to make sure that's the active window, and I'm going to click the square to run it. Okay, so again, pixel values have changed. The screen transfer hasn't caught up with that yet, so I'm going to rerun the screen transfer. And now this is looking a lot more like what I would expect. The background is really nice and clean, especially on the right side of the image. So that tells me that choosing this region here as my background reference was a good idea. For the most part, the image is nicely balanced on the background. I will have to deal with this excess color in the blue when I get to Photoshop. But at this point, I would say I want to apply the screen transfer function. I want to actually change the pixel values now. So I'm going to bring that back up, screen transfer function. And I'm also going to bring up a tool called Histogram Transformation. This is the tool that will allow me to apply the screen transfer function to the image and actually change the pixel values. And the way that is done is the screen transfer function has run and it has produced a really nice image, but again, it hasn't actually changed anything. So I want to take what it's doing to the pixels and apply it. And so to do that, I want to grab this little caret icon here and drag it into the bottom of the histogram transformation. And what that does is tell histogram transformation, okay, this is what the screen transfer function is doing. I want you to define that as a histogram transformation to the image and then apply it to the image. I know that sounds a little convoluted, but it's just basically telling you, okay, I've got this screen transfer function. I want to apply it to the image, and it's now applied. But of course, the image is still showing it as it was in the screen transform. So I have to turn off the screen transform function. Sorry. So I will click this little X here, And that turns off the screen transform. And now this is the native state of the image. It's a color combination, color calibrated. I can see that the distant galaxies are showing up a little more red, which is what I'd expect, since those are the ones that are showing up mostly in the long wavelength filters. Colors look really balanced. The cluster looks nice. At this point, I'm going to take this out of PixInsight and start working on it in Photoshop. And before I do that, I will delete all my previews. And because I have this issue in the short wavelength channels that I know I want to deal with in Photoshop, instead of saving this out as a single color image, I'm actually going to break it down into 3 color channels. So the RGB, and that's this button up here, split RGB channels. So when I do that, I get 3 grayscale images, and the grayscale images correspond to the individual color channels. So essentially what this is the B is the equally weighted combination of the 2 short wavelength channels, just as we defined with pixel math, right? Except now everything has been color calibrated, so it's not exactly that anymore. But when I take these out and combine them in Photoshop and then reapply color, I'll get back to the original color image that we have here. But I will be able to focus in on the calibration issues that are just inherent in this one channel and clean those up in Photoshop. And so at this point, I'm going to close out PixInsight and we'll bring up Photoshop and get started working in there. So we've got everything from PixInsight now loaded into Photoshop. This is actually the file that I used for creating the deep field image that was released. So this is the official Photoshop document from that release. This first layer here is actually the 3 color channels that we just wrote out from PixInsight, right? So if I were to combine these in color, I would get back to the original color image. One of the first things that I did when I worked on the data was a subtle but important step of sharpening the image just slightly. And I'm going to show you what that effect is here. Let me turn off a bunch of layers. Okay. So you may not even see it initially, but I'm going to zoom in and I need to change this to normal so that we can actually compare apples to apples. I'm using a Photoshop plugin. It's called APF-R, or Absolute Point of Focus. This is a plugin that was developed by Christoph Kautsius, and it's a really powerful but very subtle image sharpening tool that operates on multiple scales. You basically define sort of the pixel scale of how you want to sharpen the image. It'll do a sharpening routine that sort of respects that, the image scaling. So it's like a tonal sharpening at different pixel scales. And so the reason that's important is because, of course, the long wavelength channels are lower resolution than the short wavelength channels. And so you don't want to apply the same kind of sharpening all across the image, because you will then sort of emphasize things you don't want to emphasize, like noise, versus the real data. And so when I say this is subtle, I think you'll probably see that as I zoom in here and we look at one of these regions in the core of the galaxy cluster where we see these little dots. These dots around this galaxy are likely sort of the first globular clusters to form around the galaxy. And this is one of the first times we've been able to see those in a deep field image like this. And I'm just now clicking back and forth to demonstrate the effect of the sharpening on this. And it's really, really subtle, but I wanted to be sure that these globular clusters showed through really cleanly and nicely in the final color composite. So I went through and found good settings for APF-R for each of the filter combinations and applied that for each one individually. Okay, and then from here, now I know that I want to deal with the variations of the background level. So these big squares that show up as excess blue in the color composite. And the way that I did that was just actually with curves adjustment layers. And a curves adjustment layer is basically just changes the pixel values, and I'm using masks to define it in a certain region of the image. And so in this case, if I turn this on and off, you can see how it's affecting the image. I just define a box, and I'll just do that right now by hand. Let's apply a curves adjustment layer just to this region of the image. And so I've defined my box, and then I'll go to layer, new adjustment layer, curves. Use previous layer to create clipping mask. That means it'll just apply it to our blue channel. Okay, and now it just created a new curves layer here. And this white box inside the black, this is telling us that there's a mask applied, such that when you change the pixel values using the curves adjustment, it will only affect the white area and the black area will stay the same. So if I go up to my properties window here, so this is our histogram of all the pixel values in the image. And if I drag from here, this is changing the black point. So if I pull this over, you can see our square gets very black. It's also demonstrating the effect of using a mask on this image. So it's only affecting that region that's white in the mask. But the way that I want to treat this is it's going to be a subtle change, and it has to be iterative because you can't get this all in one shot. So what I do usually is I use this little hand icon up here. I click on that, and when I mouse over the image, you can see there's a little circle in the properties window, and that's showing you roughly the pixel values of where the mouse is currently sitting. And so if I want to reduce the background value slightly, I'll hover over a region of the background, click, and then I can drag down to bring that curve down a little bit. You can see that it's subtle, but it's affecting the pixel values. It doesn't have to be subtle if I pull it too far. And you can see how it's adjusting the curve on the right. And so it really is like a by eye kind of thing. You just have to go through it. And it's, like I said, it's an iterative process. You can see that my curves layers have not only a box, but I also went back with a brush and took some regions out a little bit. This is actually looking at the mask itself. So if I step through each of my curves, you can see what the effect was on the image. The reason I was using those brush adjustments here is that there is a very faint glow of starlight that sort of extends beyond the core of the galaxy cluster. And I need to be really careful about removing that. I don't want to take that out. But in terms of the pixel value, it sits sort of just above the background level. So it's really delicate. If you're reducing the background level, you don't want to take it so far down that you've taken out that star glow. So it was, again, an iterative process. I could see it there. I wanted to preserve it. And so I had to be really careful when applying these curves layers that I didn't change that. Okay, so I've gotten this to a point where I'm happy with, it's not exactly a uniform background, but it's a lot closer. And so now I'll apply color, similar to the way that Elisa applied color, using a hue saturation layer. And so now this is the blue channel. Again, the combination of the F090W and the F150W filters. So that's our blue. I did a similar process with the green channel because we still had some of those artifacts in the green as well. So there's some curves layers here dealing with that. And then, of course, the hue saturation layer to get the color. So there's our green channel. And then the red channel was actually really clean. So I didn't have to deal with creating curves layers and adjusting background levels. I just applied color directly. So there is the full color combination after dealing with some of those background level problems. And now this is like the starting point for me. I consider this like a camera raw file at this point. So I'm starting to think about this in terms of photography and how I would approach it in terms of getting contrast right, getting the tonality of the image right, adjusting color saturation to, like, for example, get these background galaxies that are right now appearing kind of orangish. I know that these really distant galaxies are going to be red because they're showing up in the red channel. And so they need to be a little redder. They need to have a little more saturation to them. Overall, the image is a little muted in terms of color. And so we'll go in and adjust that. And like I said, this becomes more of a subjective experience at this point, and it's kind of up to the individual image processor where they take it from here. And so this is where I think, a lot of people, two people can process the same data and come up with a very different image. I mean, Elisa and I have done this before. We'll both process an image and we'll compare our results. And sometimes we're shocked at the differences that we see. But I think generally we both have a similar eye for this kind of work. And so we tend to produce images that are sort of complementary to each other. And so we work together very well that way. So this folder here, color balance and contrast, that's where I do all of these steps. I'm just going to activate it so that basically that's the final image right there. But we can step through and see what is actually being done to the image. I'm going to drag this up again so we can actually see these layers. Okay, so I'm just going to turn them off all the way down the line here. And we'll start with the flat combo clean sharpen EQ. That's basically just take the image that I created, make it its own flat layer, right? And start working from there. So the next step was another background equalization. And for this one, I'm using a mask, and it's an inverse of the image. So if I click on that, you can see this is the mask that's being applied. And basically what I'm trying to do here is I want to get that background as flat as possible in terms of the color variations across it. And so I'm applying, I believe what I did to this image was a hue saturation layer where I kind of bumped off the saturation slightly so that the pixel values are closer to gray instead of color. But obviously I don't want to do that to the entire image because then I'll lose color in the galaxies and I'll lose color in the stars. So I'm using this mask, and it's an inverse of the image so that the regions that are black are not going to have this effect applied to them. And then the regions that are white will. And so, of course, because it's an inverse of the image, the white regions are essentially just the background. And so I get a really nice, clean, sort of uniform background by doing that. It's a really subtle step, but it makes a big impact later. I'll flatten the image again. And then at this point, I've made this a smart layer, and I've applied the camera raw filter. And the reason I do it as a smart layer is because I can always go back and readjust the camera raw settings if I need to. So this is camera raw. It looks like I just adjusted the white balance slightly, tinted towards green, reduced the highlights a little bit. So if I just drag this slider back and forth, you can see the effect that happens. I've taken the shadows down a little bit. I want to get the black level closer to black, but not totally black. I've increased the whites a little bit so that the shining cores of stars and galaxies are showing up, in high contrast as opposed to, or when compared to the background. The texture and clarity sliders are very powerful, but it's easy to overdo them. So I have to be really careful to not apply too much of either one of those. Texture is essentially, it's like a pixel scale contrast enhancement. And so it's looking at very small scale changes in the image. And if you bump it up all the way, you get like we call it a crunchy image. You've essentially accentuated the noise of the image if you go that far out. So I try to keep it below 20. I mean, that 20 is really high, actually. So I think I had it on 15 for this one. We'll leave it at 13. Clarity is similar to texture, but it does it on a larger scale. So it's looking for variations across like brighter regions versus darker regions, and it will emphasize those differences. And so if I drag that really far across, you can see the effect it has on the image. And you can go the opposite way and reduce clarity, and sometimes that's an interesting effect, but we're not going to do that here. So again, it's subtle. A little goes a long way. You just kind of want to pepper it in there if you're going to use it at all. Dehaze is another one that I like. It basically just takes, if you're looking at like a photograph and there's a haze in the photograph, it'll kind of remove the haze. It's basically doing another kind of contrast enhancement. But again, this can be very much overused. And so I try to be very gentle with these tools when I use them. One that I did not use here, but I think I did actually use this for another level of processing is, so color noise reduction. This is, it's a small scale effect. Let me zoom in really far. The color noise reduction will look at the variations in colors across pixels in the background level. And similar to what I was doing to try and get a uniform sort of grayish background, color noise reduction will help and go a long way towards providing that as well. It's, again, very subtle, but you can kind of see the changes. If I overdo it, I'm losing color in this little portion of the galaxy here. So if I go turn it off, there's a little bit of red, a little bit of blue in here. I crank it up a little bit, that goes away. So again, it's something you've got to be careful with. You don't want to overdo it. But all these tools combined together, I find them very powerful, and it's a great first step towards getting towards the final version of the image. These next few adjustments are, so this next one here is, I noticed there's a little bit of an excess blue in the core here. So I used a mask and a curves layer to reduce the core blue. I did another contrast adjustment here. This is what we call an S-curve. That's lowering the background level a bit and then pumping up the brights just slightly. And that's just, again, to give us a contrast adjustment. Basically, I'm making the sky a little bit darker. I don't want it to be black. I mean, this is kind of a personal preference, but when I'm looking at images of space, if the background is totally black, it just doesn't look natural to me. In an image like this one in particular, I worry that I'm cutting off faint galaxies that are way distant in the background. They could just be clobbered by something like this. So I want to always have just a little bit of signal in the background level. And if I'm looking at the info window, as I'm mousing around the image, you can see that the RGB values are showing up here. And when I get to the final version of the image, I want those to be sort of in the realm of 10 to 15 in terms of pixel values for the blank sky background. So that's what I'll be looking for when I get there. Next step is a saturation adjustment. This is to really help emphasize those background galaxies that we know are showing up in the red channel. I'm looking to get that color to pop a little more. Again, it's a subtle effect, but it is an effect. And the actual adjustment layer that I'm using here is called a selective color, which allows you to go in and sort of hone in on specific colors within the image. And so in this case, the reds, I'm adjusting the reds a little bit to bump up the saturation of just the reds in the image. And that helps bring out those galaxies a little more. So we'll back out again. This slight sharpened luminance layer is a very subtle thing that I sometimes do. You can see it's only applied at a 20% opacity, so it's a really subtle effect on the image, but I'm using it as essentially taking a copy of the image as it is from this point, placing it on top of itself, and then setting it as a luminosity layer. And this is just something I've picked up over the years. I do it sometimes I don't do it. It's like a personal preference thing. When you get to this level, you're doing things that will help pull the image together and create what you sort of see in your mind as the final version of the image. And sometimes I just try things out and see what works and what doesn't work. And this was one of those things where I kind of liked it. I kept it at a 20% level. Honestly, it probably wouldn't matter if it wasn't there. But I did like the final version of the image after doing that. This is another really subtle change. I think I was seeing some issues in the core of the galaxy cluster, and I just wanted to adjust the saturation. Again, I'm looking, there's like an excess blue in there, and I'm trying to get rid of. That was really bugging me as I was finishing up the image. So I'm using a masked hue saturation adjustment there. Final cosmetics this would be using the clone tool to just get rid of a few little cosmetic problems in the image. I'm going to hone in on this one down here. This effect is called persistence, and it's basically this bright star is repeating itself across the detector different times. And these ones are outside of my crop, so I don't care about those, but I did want to get rid of this one here. And so I just used a very slight adjustment using the clone tool. I try not to use the clone tool in images because we don't want to introduce things that aren't there. We don't want to take things away that are there. It's all about respecting the data. So the clone tool is used very sparingly, only to remove artifacts that we know are not inherent in the data. They're an artifact of the optical system of the telescope. In this case, we have this persistence effect around bright stars. And so I can use the clone tool to just clean that up. And you can see it's really subtle. There's also a hot pixel here that I'm removing. I know that that's another artifact. And this is another effect of the persistence. So all three of those are being removed in this step. And then the final step is one last curves adjustment. This is a really, really subtle change in the overall color. And the way that I'm doing that or applying it is I just want to make sure that my background is as neutral as it can be. And so I use the curves adjustment layer with this little dropper tool. You use this to set the gray point of the image. And you can define that in terms of a point sample. That's what we got here, a 3x3, 5x5, all the way up to 101 by 101. I would probably do 11 by 11, and then just click in a region of the blank sky, and the tool will automatically adjust the whole image according to that 5x5 or 11 by 11 box in terms of making the whole image have a neutral background in that region. And so that was the tool that was applied at the end there. And then finally, I have defined a crop region. That's what these lines are. I can turn those off. You can see that the filters didn't quite line up completely across the whole image, and that's totally normal. We see that all the time. So you obviously don't want to include all that extra ratty stuff around the edges. So I would define a region to crop that out. And before I've actually saved out the final version of the image, I'll just make a box around that and make it black so that I don't see it. So that gives me the idea of what the final image will look like. And so when I do save out the final image, I'll use this to actually crop it to this box. And we'll use image crop for that. Okay. And then there is our final image.
Wow. I mean, holy moly, that was amazing, Joe. Thank you. Your attention to detail, your persistence and patience, and just looking for even the most subtle tweaks that can be made. And I think that's something that you really were able to demonstrate for us, is that so many of these changes to the images are extremely subtle, extremely gentle, and they're so subtle that nobody would notice, except for the fact that if you didn't do it, they wouldn't necessarily notice that it was wrong, but they might not necessarily buy into the image as well as we can. The result is so natural and so beautiful and so incredibly detailed, and this was just an amazing demonstration of, I know not even all of the work. I mean, I know this is not something you do over the course of an hour. How long does it take you to actually work up an image like this from start to finish?
So for this version of the deep field image, that took about 4 hours from start to finish. But I will say that was the fourth time that I had run through the data. As we alluded to earlier, we were working with the scientists here at Space Telescope to reduce the data and to get a clean version of the images as a starting point. And that in itself was an iterative process. The calibration files were sort of improving as we were moving through them. And so we had different versions of the original data to work with. And so for the deep field image, we actually had 4 different processes. So by the time we got to the 4th version, I got pretty good at processing it. I'd say the first few times took maybe a whole day, like 8 hours to get through the whole image. But by the time I had done it the 4th time, I kind of knew what I wanted it to look like. I knew where I was going. I knew how to run through all the steps. And so I was able to do it in 4 hours. But that's kind of a record, I think.
Well, the result is definitely worth every second of those hours. Thank you so much, Joe, for demonstrating that for us.
Oh, thanks, Christian. Thanks for having me.